feel that the working is not clear, you need some explanation here and there, because for now you need more practicing of question paper so you get different tricks in terms of concept. Now you know here and there the concept. That's why we are revising. But some of the concepts I can see you have mastered them. The only thing that is left is just doing more of question papers to just see different tricks here and there so that you master all the tricks. So yesterday on rate of reaction, we ended here yesterday where we wanted to analyze. So the graphs below labeled A, B, and C show results of 3 experiments in excess. So just share this one. Okay, sorry, I just muted. Wanted to attend to something. So let's start. So the 2 graphs below labeled A, B, C show the results of 3 experiments in which excess sodium bicarbonate. So you must know the formula for sodium bicarbonate. Sometimes they are not given. Do you know it? Hello?
So I didn't hear you properly. The network wasn't good.
No, I'm saying sometimes you must know the formulas of sodium bicarbonate, the molecular formula. I am saying, do you know the molecular formula?
Yes,
the molecular formula for sodium.
Of what? So can I please change can I change the Wi-Fi quickly, because this one I'm using is not working.
Okay.
So can you please repeat what you said?
No, I was just saying the formula, the chemical formula of sodium bicarbonate. What is the chemical formula or molecular formula for sodium bicarbonate? This one.
NaSO4. SO4.
SO4. Are you sure, or you're just guessing?
Is it 3? I'm guessing.
Yeah, guessing. So you must get familiarized with this one. And another name for sodium bicarbonate. What is another name for sodium bicarbonate? Sometimes
Table.
they use
Table salt.
No. Table salt. Table salt is the common salt, which is sodium chloride. The common salt, the one which I am referring to, that one. So for sodium bicarbonate, this is what you call at home. And they tell you, go and buy what?
Soda.
Yes. So that is what
Yeah.
sodium bicarbonate. Okay. And the molecular formula, sodium bicarbonate. Okay. So we must know also how to write. Sometimes they will say, give the reaction sodium bicarbonate reacted with this to produce that. So we must be in a position to write the number of moles you are able to calculate since you know the molecular formula, etc. So that is what we refer as to soda, baking soda. So normally it's for baking. One which they use for baking. Okay, so the question itself, those two graphs. So in which excess sodium bicarbonate reacted with 200 cubic centimeters of 0.1 moles per cubic decimeter. So we are given the volume and we are given concentration, isn't it?
Yes.
Yes, so this is our volume and this is the concentration. And if I'm to ask, what is 200 cubic centimeters in dm3 in cubic decimeters?
It's 0.2.
It will be
0.2.
0.2 decimeters, cubic decimeters.
Yes.
So 1 cubic decimeter, 1 cubic centimeter is how many cubic decimeters?
1,000 cubic centimeters.
1,000. Okay. So you should also know how to convert that to moles per dm3 because that volume must be converted to cubic decimeters since it's not in cubic decimeters. And you must also use your knowledge of 200 milliliters. 200 cubic centimeters is the same as 200 milliliters. Okay, let's go to our question. On the vertical axis, we are given the volume of gas. And on the horizontal axis, time, which means the reaction with time. So which graphs A to C would match the reaction conditions shown in the table below? So which graphs? A, B, C, which means we have two graphs, A, B, and C. A, B, and C. If we move backwards, I've moved faster. Between A, B, and C, which matches? Let's scroll backwards. Yeah, we are here. So we want to match which one could be A, which one could be B, which one could be C. Let's start with the first one. And the 25, 0.1, and the 200, what are they representing?
200 represents the 200 represent the volume, the 0.1 represents the moles per cubic centimeters, and the 25 represents the rate of reaction.
So we don't have temperature, or we don't have time.
We do.
So which one could be matching the time? Because I am seeing there is time when, and also the volume of gas which was produced, and on the volume of gas which was produced, we are not having any volume that is reaching 200 or 300. But, so what could be those values be? Because they are not indicated, what could be the values be? But for 0,1, for concentration, you are right to say when we increase the what? The concentration. They want to see what happened when you increase the concentration. But those values which are 25, 40, 40, what are they? So that we are able to analyze. Because once we don't know the values, we won't be able to analyze. So this question, there's some information which should be missing, and the table should supposed to be labeled. For C 2.1, the temperature of the system has decreased. Thus, a lower rate of reaction due to the less number of collisions per unit time. So which means, were you saying the rate of reaction is the first one?
Yes.
So which means the rate of reaction to be what? Remember, we measure the rate of reaction in what? What are, how do we measure the rate of reaction? The units are what?
Moles per cubic centimeter. We measure rate of reaction in moles per cubic centimeters per second.
Per second. So which means in our case, the temperature of the system is decreased for C. Thus, a lower rate of reaction due to the less number of collisions per unit time. So which means they are saying what could be the possible reason why C is moving like this, C. So we can see that C, there is a possibility that the temperature is low for C. And then for A, the concentration. So the concentration of the acid, they doubled. That's a greater reaction due to more collisions per unit time, as well as more gas produced being due to more reactant of the particles, reactant particles per unit volume system. So for A, they are saying the concentration, if the concentration of the acid is doubled, which means now we can produce more volume of hydrogen gas. Then for B, what could have happened for B? The reaction rate will remain the same as both the temperature and concentration remain the same, increase in volume of gas produced using a greater volume of acid. So which means 2.1. 2.1 is matching with C. So let's come and verify 2.1 is the one that is matching with C. And then 2.2 is the one that is matching with A. We want to analyze this now. And then 2.3 is the one that is matching with B. So let's go to the graph. We check and we contrast these answers to see if they are tallying with the theory. All right. So A is the fastest. Why? The concentration had increased. Is that correct? From 0.1, now we use the concentration of acid to 0.2. So which means A has to be the fastest of them all. Does it make sense to you?
Yes.
So which means A has to be the fastest because the concentration has increased. So here the volume, so which means the last table is indicating the volume. That's what I was saying, that there should be information. So this is the volume of the acid which was used. And this is the concentration of the acid which was used, of HCl, or the concentration of the acid. Then what about this 25? You did not tell me what is it about. Is it the reaction rate? Is it the volume of gas which was produced? What is the 25? And if we check, when you say A produced more than the volume of the gas, more than 40. So which means we can't say is the volume of the gas. What could A represent? Can A be, can the first row be representing reaction rate? The concentration of reactants or products, not the concentration of the acid. Is that not so?
Mm.
So if it's the concentration of the reactant over the time, what is the time?
The time for what?
Remember, reaction rate, it has to be the concentration over time. So if you want
Yes.
how they obtain this 40 and 25, how they obtain the 40 and the 25.
I think we look at the graph where the reaction has came to an end.
Where the reaction is coming to an end.
Yes.
But here you can see for A, the reaction is coming to an end somewhere there. That is for A. And for B, the reaction is coming to an end somewhere there. And then for C, you can see it somewhere there. So where are these values coming? Because we don't have a value which is more than 40 on the column. Yet for A, we are having more than 60 there. So that's why I'm saying, what could these values be representing?
The time.
The time. So which
Yes.
means, all right, the time it takes to what? If you say it's the time, to be the time for what? To
The
produce.
time it takes for the reaction to come to a stop.
But if you use 40, if it takes 40 seconds, and then for this one, for A, we are saying the reaction, it took 25 seconds. So which means to produce products.
For A, the reaction took 40 seconds. And for C, the reaction took 25 seconds. And for B, the reaction took 40 seconds to come to a stop.
Because it does not make sense, actually, to me, if what you are saying now, because if you are to check if something is having a higher concentration, which means the reaction rate has to be faster, isn't it? The time,
Yes.
the time we take to produce hydrogen gas, it must be the fastest time, which means less time. Already we are producing a volume of gas. So how come yet our concentration is higher and we are taking again a higher time for us to produce a hydrogen gas? Because if your concentration is higher, which means you are making the reaction to be very fast, instead of taking long to produce the same amount of volume, you are going to take less time. You see? So that either it could be the reaction rate, but it can't be time. Reaction rate or the temperature. Reaction rate or the temperature. By saying for B, if you are comparing between C and B, C was at a lower temperature compared to what? Compared to B. If you compare C and B, why is C lower than B? C is lower than B because C is at a lower temperature of 25. And then B is having a higher temperature. That's why the reaction was a bit faster. So the first column, it has to be talking of temperature. This definitely has to be temperature. It can't be time. If you make it time, it does not make sense, because the one that should be having the highest concentration should be the fastest. So, but in terms of temperature, if you increase the concentration and also temperature, which means that has to be the fastest reaction. And if you compare C and B, we can go with the one which is B to be the fastest compared to C, because C is at a lower temperature. So which means from the explanations, now they can tell that the temperature of the system is the lowest at C, and the concentration of the acid was the highest at A. And then for B, the one for B to be the second one compared to the rest. So I don't think it should be the reaction rate. I don't know if you are getting me.
A little bit.
It has to deal with temperature. However, it's because the table, they did not put values, so it can be debatable here and there, but in actual sense, it was not time. All right, let's talk about this Boltzmann distribution curve. All right, so where we are having the activation energy, the minimum amount of energy. So when they talk of activation energy, the minimum amount of energy needed for successful or effective collisions to occur. So on your graph, if you are given this curve, so on your left-hand side, obviously you are having the number of particles. So these are only the particles where they could overlap, which means which were after the activation energy. So with these particles, which are going to be on the left-hand side before the dashed line, are the particles which were not having enough energy to react. So after the activation energy, that's when we have only few particles that manage to produce some products due to overlapping and effective collisions. So this diagram must just know it's diagram of number of particles versus kinetic energy. So normally it just asks you to either they will say draw what does this line represent, the dashed line, then you label. So draw the graph of kinetic energy versus the number of particles. So this is how you should be drawing it if it was asked. So this, right. And then also when you are given two scenarios which means you are drawing again the number of particles. And here we still have our EA, which means the activation energy at this point, EA, activation energy. So your activation energy, after the activation energy, we are seeing that if the graph, for this graph, let's use different colors. For the red one, the number of particles which are below, which is at high temperature, the one which is at high temperature, it has more particles. So by more particles, we are referring to this surface area, which is bigger compared to the surface area of particles which are only under the curve of a low temperature. So this is only the area. There are few particles at low temperature. And then at high temperature, which means we are having more particles which are able to form effective or successful collisions due to high temperature. So this is the way the diagram should be, which means the number of particles versus the kinetic energy. So at high temperature, we are having more particles with high kinetic energy. That's what it means. And at low temperature, we are having few number of particles. So it's similar to the one which we drew first, but the one which we drew first, which I displaced first, it was only having one curve, where we did not have two temperatures, where we are comparing the number of particles versus kinetic energy at high temperature and low temperature. So this is the diagram which you should draw at high temperature or low temperatures. So the marks, they are just coming, labeling your horizontal, labeling your vertical axis, and indicating the number of particles and the position of the activation energy. Okay. Then from this one, you are having your reactants. If indicating the activation where you use a catalyst. So here, these are your reactants. When you start by having reactants, where you are having enthalpy change. So these are our reactants. And then your products, what you are going to form here is where your product is going to be on that line. So this is the product. So the maximum height, what do you call this height? At this point, we call it what?
Activated complex.
So there is the activated complex, which is correct. So there we are having our activated complex. So this diagram is simply indicating the effect of adding a catalyst. You say the catalyst just lowers the activation energy and it is speeding up the rate of reaction. And the catalyst does not get used up. So if I'm to ask here, the change in enthalpy, is it a positive or a negative change here? Regarding where we started, is it a negative or a positive change? The enthalpy, the delta H. Which sign should I put there? Should I put negative or positive delta H? So that
Negative.
to be a negative because the enthalpy of reactants minus the enthalpy, the enthalpy of products minus the enthalpy of the reactor. So it will be a negative. And what can you say about this type of reaction? Is it exothermic or endothermic?
Exothermic.
It will be exothermic. So these are the things that you should know on this type of graph. It will be an exothermic reaction. So the question when it comes tells you if a catalyst was added, how is the graph going to change? So you put it a dashed line. So from the solid line, we are having a reaction where there was no catalyst. So activation energy from reactant to the activated complex So the activation energy is very high as compared to the activation energy when a catalyst was used. So you indicate the dashed line that to say, no, the activation energy just lowers the minimum, the catalyst only lowers the minimum energy which is required to convert the reactants into products. Okay. Negative delta, exothermic reactions. So you must know that. So you have been told that the reaction is exothermic. So the reaction is exothermic. You are correct. So the reaction is going to be endothermic if the delta H is positive. Okay. So these are the rates of reaction. So now we are having another distribution curve here of kinetic energy versus the number of particles. So you want to check which graph. A1 is representing an activation energy of uncatalyzed reaction, which means the activation energy, EA1. We are having few number of molecules, few particles, number of particles, which we are forming, which are resulting in effective collisions. So which means that reaction, EA1, it was not having a catalyst. But at EA2, you can see the region that from here, from there, going upward, the number of molecules which are after, there are more. So which means there was a catalyst which was added. So that is the idea that we are explaining here. So EA2 representing the activation energy of the catalyzed reaction. So when the question comes in an exam, it will tell you, indicate where the catalyst was used and where the catalyst was not used. So for EA2, which means that activation energy number 2, a catalyst was used. Why? Because thereafter, we can see that there are more number of particles which are resulting from effective collisions or successful collision. But from EA2, EA1, we are having less number of particles. So no catalyst. Then for EA2, there is a presence of a catalyst. Those are the simple things that you should also master. I don't know if you're having a question there in terms of the graphs.
No.
In terms of the graphs, you are fine. So catalyst increase the rate of chemical reactions, and then catalyst function by providing alternative energy pathway in the reaction by lowering the activation energy. They do not undergo any chemical or physical change. Catalysts do not change the size of enthalpy of the reaction. Catalysts do not affect the amount of product formed. So the amount of product formed is not determined by a catalyst. So it's just to speed a reaction. Time. A catalyst you check with time. So if the rate of reaction is faster, which means a catalyst was used, but the amount of hydrogen or volume of gas produced, it remains the same. Okay. So these are some of the key things. Activation energy, which means the minimum amount of energy required for a reaction to take place from our graph. EA, activation energy. What effect does a catalyst have on an activation energy in a reaction? So like what we discussed, it catalysts to lower the amount of activation energy need in a chemical reaction to have a successful collisions. Okay. What chemical or physical change happens to a catalyst during a reaction, which means there is no any physical change, no change at all. So these are the basics. Briefly explain what is a Maxwell-Boltzmann distribution curve is and what is the importance of this type of graph. I want to hear it from you. This one. Do you have any idea of What can we get from the Maxwell-Boltzmann distribution curve? And what is the importance of this graph?
Which, can you please go back to the graph so I can?
I must go back to the graph
Yes.
or the diagrams. This one. There's this one.
Thank
And there's also these ones as well. The effect of temperature on the Maxwell-Boltzmann distribution. So where it talks about the kinetic energy and the number of particles. So here we are analyzing two things: temperature, high temperature and low temperature. And then here we are analyzing effects of a catalyst. Then this is just the issues of activation energy, where we used a catalyst and the other one no catalyst. So the question now is saying, briefly explain what is meant by a Maxwell-Boltzmann distribution curve and what is the importance of this type of graph? What can you say?
you. The importance of Maxwell-Boltzmann distribution graph is that it shows us the particles and the speed of distribution. And it explains the effects of temperature, concentration, concentration, and I'm not sure about the last one. And
Okay.
I'm not sure.
Yes, it's good to try. So what is it? This is just a graphical representation of the distribution of the number of particles within a system based on the amount of kinetic energy they possess. It is important as it allows one to see how many particles will possess the minimum activation energy required for a successful collision per unit time to occur. So you are able to see how many particles. So that is the importance. Okay.
Yes.
So you add to what you have said. You add to what you have said as well. Some questions we have attempted activation energy. And this is the activation energy at high temperature. EA, we have done that graph. So more molecules will have kinetic energy, which are greater than the activation energy. So by a larger shaded area under the curve, this will lead to more effective collisions per second, which leads to a faster reaction rate, which means at higher temperature. So the dashed line indicating the activation energy, EA. Activation energy, EA. All right. So we are given question number 2. Students conduct the following experiment: copper 2 oxide and sulfuric acid. So copper 2 oxide, CuO plus sulfuric acid, H2SO4, to give copper sulfate plus water. Okay, so that's what we are having. So H2S4 is allowed to react completely with an unknown mass of copper 2 oxide at a temperature of 50 degrees Celsius. The potential energy profile for this reaction is illustrated below. That is the potential energy profile, which is the diagram of potential energy versus time. The other one, which we were dealing with, it was kinetic energy versus the number of particles. So we are having reactants and we are having products, units in kilojoules. So the first question now, is the reaction exothermic or endothermic?
Exothermic.
The reaction is what?
Exothermic.
Yes, these are our products, these are our reactants, which means the enthalpy change. It's
The enthalpy change is
negative
negative.
H, delta H, yes. So which means it's an exothermic reaction.
Mhm.
Yes, it's exothermic. So we have chosen exothermic, which is correct. So the reaction is exothermic. And heat exits the system, which means heat is released during an exothermic reaction. Then from the diagram, calculate the activation energy required for the reaction to take place. What is the activation energy required for this reaction to take place? So calculate the activation energy for the reaction to take place. What is that activation energy? EA is equals to
20. EA is equals to H activation complex minus reactants, which is 58 kilojoules.
which is 58 kilojoules. So from here to the maximum, that is our EA, the activation energy. So you need 58 kilojoules. Which is correct there. So that was the second question, 58 kilojoules, which is correct. And then what is the change in enthalpy for this reaction? So in change for enthalpy, which means you are looking for which symbol? Delta what? Delta H.
Delta H.
So what is the enthalpy? What is the change?
Can I please see our values?
Yes, let's go back to the values. Let's go back to the values. What is the change in enthalpy?
Negative 35 joules.
Negative 35 joules. So the change in enthalpy, negative 35 kilojoules.
Kilojoules.
That is correct. 2.4. The concentration of sulfuric acid is decreased. So using the collision theory, explain what will happen to the reaction rate. So is it going to be faster? Is it going to be slower? The reaction rate, if the concentration of sulfuric acid is decreased.
It will be slower.
To be slower. Yes, so use now the theory, the collision theory, to explain how concentration.
If the concentration is decreased, then the amount of particles per unit time is also the amount of particles per unit volume is also decreased. Hence, more particles with enough kinetic energy, and the more effective collisions take place per unit time, and the rate of reaction will increase.
Okay. So, like we indicated, decrease in concentration will result with fewer collisions per unit time of sulfuric acid particles with copper oxide particles, which means the sulfuric acid particles are colliding with the copper 2 oxide particles. This will lead to decrease in reaction rate. So, which is correct? Yeah, which is correct. All right. So this was chemical rate of reaction. There is nothing more that we can add. We have done it. So we are moving now to the chemical equilibrium, isn't it?
Yes.
Chemical equilibrium. So we browse through the chemical equilibrium. So for chemical equilibrium, so according to Le Chatelier's principle, which means a change in any of the factors that determine equilibrium conditions of a system will cause the system to change in such a manner as to reduce or to counteract the effect of the change. So this is not the only definition. There are many definitions. Some they will say if there is a change on a system according to Le Chatelier's principle, the system will counteract that disturbance. So that change, some books, they write it as disturbance, whatever. But the key term is that what is it going to do according to Le Chatelier's principle, which means the system will cause the system to change in the manner to counteract the effect of change or to counteract that disturbance. So if the disturbance made the system to go up, so according to Le Chatelier's principle, the system, it will counteract that disturbance to bring it back to normal. So they always work in the opposite, to counteract, which means to reduce, change that effect. So there are key things that you should know about the open system. An open system, matter and energy can enter and leave the system. But if it's a closed system, matter and energy cannot leave the system. A forward reaction is a reaction that takes place when reactants are converted into products in a chemical system, which means just a forward reaction. But a reverse reaction is a reaction that takes place when products are converted back into reactants. So it's the reverse. And then reversible reaction, which take place when reactants are converted into products and products are able to be converted into reactants. That is reversible reactions. Any question there?
No.
Then dynamic equilibrium, chemical equilibrium. This is when the rate of forward reaction is equals to the rate of reverse reaction in a chemical system. That's when we say it's dynamic. Dynamic in the sense that it seems to be equal, not moving, but it's already happening. It's still going forward, and it's like chemical equilibrium has been established, but the reaction is still going in both directions. it has not stopped. It's still occurring both forward and reverse. That's why we are using dynamic. Then evaporation, the process of phase change whereby liquid particles are changed into gas particles. Condensation, the process of phase change where gas particles are able to change back into liquid. So those are the things that we should know. Equilibrium constant expression, which value, which symbol do we use for equilibrium constant expression? This one. Which symbol do we use for this mathematical ratio, which expresses the ratio of products of the
KC.
the concentration of reactants? KC, yes, that is the KC. So KC is the concentration of what? Products over the concentration of what?
Of reactants.
So, so that is the KC value which we are talking about. Okay. So let's see. Very simple things. So we can finish this chemical equilibrium by tomorrow. All right. So an open system and a closed system where matter and energy can leave the system, it's not closed. But here now we are having a closed system, which means it has been blocked. This one was an open system. You can see that it's open. There's nothing closing the beaker. But the second one, the beaker now is closed. It's closed system. Right. Reversible reaction example, when you boil water from liquid to gas, then gas back to liquid. So those double arrows, they should be of equal length when you're writing them. Don't choose the other one is bigger, then you put a short one like this. No. They should be of equal length. That's what they're just saying. Right? So dynamic equilibrium, which means it's happening, that refers to two opposite processes that are occurring simultaneously, and dynamic equilibrium refers when the processes occur simultaneously, processes occur at the same rate, which means the forward reaction and the reverse reaction are occurring at the same rate. Then it's dynamic equilibrium. But when you are talking of equilibrium only, it's when two opposite processes are occurring simultaneously. Then it becomes dynamic if they are occurring at the same rate. Okay. So let's have a question here for reversible reactions. Then we analyze it according to Le Chatelier's principle. All right. So these are just definitions which we just made: reversible reaction, closed system, definitions. All right. How do we represent a system in a dynamic equilibrium? Use the equation below. So A plus B, you give C plus D, which means we are having your reactants on the left, then products on the right. Those are the double half arrows. So it's a half arrow in the sense that it's not a full arrow. It means like this. Then this one like that. So that's how you write it. So don't use the full arrows. Normally use the half arrows.
Arrows.
Yes, those arrows. Yes. Name the three factors that are able to change equilibrium position of a system in dynamic equilibrium. So
Concentration, temperature, and pressure.
yes, these ones, they change. Concentration, temperature, and pressure. Okay. But when we're talking of reaction rate of reaction, what are the two factors are not included here?
adding a catalyst and the nature of
reactants.
yes.
The surface area, yes, when we are talking of reaction rate. But the ones that only affect the equilibrium position on a system is only concentration. Then you talk of temperature. Pressure only involves
gaseous
systems only. And concentration of solids normally, what is the concentration of solids? When you are calculating Kc to solid,
we don't include
solids, yes. So those are the tricks you should be aware of. So Kc, how we are going to calculate, suppose we are given, right? We are given including coefficient. This is our equation. A is a coefficient when you are balancing the equation. And B is the coefficient, C is the coefficient, small letter C, small letter D is that coefficient. So when you are putting calculating your Kc value, what they are simply saying there is the Kc. Don't forget to put the exponent to be the coefficient. For example, the concentration of the products. So these are your products. C plus D are your products. So when you calculate Kc, you multiply. It will be C to the power of the coefficient and D to the power of the coefficient, which was in front. Yeah. So don't forget this one, they are important, okay? Over the reactants, A plus B, so Kc is the product. By product, concentration of product of reactants, product of products. So you multiply the concentration of reactants, the ratio of the concentration of reactions to the concentration of products over reactants. So the coefficients are very, very important. Once you miss to balance an equation, even the Kc value, it won't come up correct. All right. So we are given here. So if you want to calculate the Kc, which means the concentration of that ammonia, the concentration of the ammonia, and then you square over the concentration of the hydrogen and nitrogen, then you multiply to the power 3, and here the coefficient is 1. The coefficient in front is 1, that's why it's to the power 1, then it's just 1. Any questions there in terms of calculating? Fine. So we are having here, like I was indicating, what is the concentration of solids? So these are our product. The product, we are having carbon monoxide, and the coefficient is a 2 squared. But for solids, we said we ignore them, which means we just consider that the concentration is just what? 1, isn't it? That's why we are saying you ignore them, isn't it? They don't have an effect because we are going to put a 1. It's just the same as ignoring it, but not a 0. Is it clear?
Yes.
It's not a 0. Okay. So now we are given the concentration of hydrogen, concentration of iodine, and then concentration of hydrogen iodide. Then you make use of the formula to calculate. Okay, so let's just warm up. We see how you calculate this one. So we are given the equation. This is our equation. These are our values. So the question is now, we have to calculate the Kc value. After reaching equilibrium, the reaction mixture was analyzed and the following concentration were measured. So the temperature. So the question, hydrogen and iodine are mixed in a closed vessel, reaction vessel, and are allowed to react at a constant temperature of 425 degrees according to the following equation. So these are the situation. Calculate the value of the equilibrium constant at this temperature, Kc. So let's just warm up. We see how we are going to go about it. What is your Kc?
It's 23.77.
Okay, 23.77. All right, which is correct. So that is the setup. Concentration of the products over concentration of the reactants, and don't forget to square the hydrogen iodide concentration. That's very simple. Just a matter of. So if you get a Kc which is equals to 1, this means that the starting and finishing concentration of both reactants and products are the same, which means both forward and reverse reactions are equal from the start of the reaction. That is Kc of 1. That is the Kc of 1. And then also, if the numerator, product concentration, and denominator reactant concentration are equal, the Kc value is equals to 1. Then if a large numerator and a small denominator, then the Kc will be greater than 1. Then if there's a small numerator and large denominator, Kc will be less than 1. So you must know those mathematical, what it means. When Kc is greater than 1, it indicates that more product is being formed. And when Kc is less than 1, it indicates more reactant is formed during the reaction while using up the product. So you check which direction in terms of your Kc. So this means that the reverse reaction has been favored before dynamic equilibrium is established. And for Kc greater than 1, this means that the forward reaction has been favored before dynamic equilibrium is established. So these are the theoretical concepts that we must master as well. All right, so here we are supposed to calculate the Kc. And remember, here now we are not given the concentrations. What are you supposed to do? We are supposed to find the concentration on your own. Okay.
Yes.
So 0.5 moles of hydrogen, 0.5 moles of oxygen are placed in a 200 cubic centimeter container at 150 degrees Celsius and allowed to react to reach equilibrium according to the chemical equation below. At equilibrium, 9.6 grams of oxygen remains. Calculate the Kc for the reaction. So we'll start tomorrow. If you want, you can screenshot it, then you look at it, That's where we are going to start from tomorrow.
Okay.
So if you want to work on it, you can screenshot it. Then we start asking you what was your answer for KC. Then we start from there. Okay. So we can stop here for today.